Hello, and thank you for joining me today for our introduction to acids and bases. So at the end of today's video, you will be able to define and explain the term ionization. Step 1, explain and define ionization. 2, you understand and the differences between acids and bases on the pH scale. So I give you the pH of a substance, you can tell me if that's an acid or a base. You have to recognize properties of acids and bases, and you're able to describe what a buffer does and what it's made of, what it's composed of. So that's the goal for today, and let's get started. So first, when water collides with itself, some of the molecules ionize or become ions. So if we have H2O plus H2O, these two come together, they form ions. So this first one, H3O, this is called hydronium, which we're going to reference when we talk about acids and bases. So hydronium is the ion that forms when two water molecules collide along with the hydroxide ion. If we just had one water molecule, it would split into just a hydrogen ion and a hydroxide ion. So hydronium and hydrogen are not the same thing, but they function the same way. I use those terms interchangeably, just as far as what we use for calculations. But though it's hydronium is H3O positive, hydrogen is just obviously H positive. This is ionization. We have another term we call dissociation. So dissociation is when you separate separation of ions. So if we put salt, NaCl, into water, remember sodium is a cation, it's got a positive 1 charge. Chlorine's an anion, it's got a negative 1 charge. When we put it into water, these water molecules surround and dissociate these ions. So sodium chloride is going to split into a sodium ion and a chlorine ion. Likewise, if we use calcium chloride, calcium's positive 2, chlorine's negative 1, so I have 2 of these. So this is going to dissociate into Ca, positive 2, and I get 2 Cl negative 1s. In this case, we're going to always assume, 100% dissociation. We'll talk about times where it's not 100%, but for right now, these will all be 100% dissociation. Again, we're going to talk about water, and that when water ionizes, H2O plus H2O, we get this hydronium here, and we get a hydroxide. This is going to be the telltale sign between whether I have an acid, a base, or a neutral substance. This is the only difference between those substances as far as reactions are concerned. So in pure water, pure being distilled, not tap water, but distilled water, we have our concentration of hydronium. These brackets, remember, mean concentration. So anything in brackets is referring to concentration and molarity, typically. But our concentration of hydronium is going to be equal to our concentration of hydroxide. So I have equal amounts of hydronium and hydroxide ions in the water. If this substance is acidic, I'm going to have more hydroniums and fewer hydroxides. So more hydroniums than hydroxides in this solution. And if it's basic, it's going to be the opposite. I'm going to have more hydroxides than hydroniums. One of the ways we're going to talk about the acids are classified as they donate protons. And so because they donated this proton, I have more hydroniums here, more protons to bond with more water molecules to make more hydroniums. Whereas bases accept, so acids donate protons, bases accept protons. And that's one of our classifications. We're going to talk about those here in a little bit, but for right now, that's enough to get us going. When we talk acids and bases, one of the things we talk about is we talk about the pH scale. And so this pH scale we reference, we'll talk about later on, but goes from 0 to 14. 0, anything low on this scale is considered acidic. And halfway between 0 and 14 is this magic number 7. 7 is pure water, is the pH of pure water. At a pH of 7, you have equal concentrations of hydronium and hydroxide. I can't write over off to the side. But hydronium is equal to hydroxide concentrations. That is your pH of 7. So because our acids are lower on the pH scale, remember acids have a greater hydronium concentration than hydroxide. So everything up here is going to have more hydroniums is going to be greater than my hydroxide concentration. And some examples, some common examples. Stomach acid has a pH of between 1 and 3. Lemon juice, obviously, lemons have acids in them, which is the citric acid. We have vinegar, which is acetic acid. Wine is slightly acidic. Grapes, orange juice. Our normal rain is actually slightly acidic. Normal rain doesn't have a pH of 7. It's got different solutes in it, and it's got a pH of less than 7, so it's slightly acidic. Milk is up there, same with pH balanced shampoo and coffee. Basic substances, anything that has a pH greater than 7. So from anything 7.1 up to 14 is considered basic, at least slightly. When you get up into the 13s and 14s, you get your strong bases. So we talk strong acids up here, which is stomach acid, HCl. Strong bases include things like sodium hydroxide, which is used for drain cleaner. But your other substances, things like eggs, seawater, baking soda, all have pHs between 7 and 14, somewhere in there as well. And again, these guys have concentrations of hydroxide that are greater than concentrations of hydronium. And that's important, and we'll talk about that more here moving on. But that's just kind of a basic overview. To determine pHs just on a rough scale, we can use what we call indicators. So these are indicators that we can use. So in lab, we're going to look at some of these. I use a lot of phenolphthalein. And so phenolphthalein is an indicator that tells you the pH of a substance. If your substance remains clear, looks like water, that substance has a pH of somewhere between 0 and roughly 8. Give or take a little bit, somewhere in this range, somewhere between 0 and 8. So it doesn't give you a real specific pH, but it gives you a range. If you get to a slightly pink color, you have a pH of between 8 and 9. Anything dark pink is going to be greater than 9 and 10. But that's this indicator will change colors based on the pH of the substance. And we're going to look at that in lab, and we use these to tell when we have neutralized our acids or our bases accordingly. We can also use things like bromothiamyl blue. We can use methyl orange, methyl red, thiamyl blue. All of these are different indicators. Some of them, such as this thiamyl blue, if it's red, you have a pH of between 0 and 2. If it's yellow, you have this range in here where you're somewhere between 2 and 9. And then if it's blue, you know that you're above a pH of 9, up in the 10 to 14 range. Those are different indicators that you can use. To prevent large, drastic changes in pH, we use what are called buffers. So buffers are substances that resist these drastic changes in pH levels. And these are used, our body uses a lot of buffers, nature uses a lot of buffers that prevent these drastic changes. And they are made from weak acids bonded to weak bases. They create this buffer that they accept some of the hydrogens and take out some of the hydrogens, so they balance out that pH. They minimize the impact of adding acids and bases to a mixture and allow that change to be rather gradual. When in nature, however, though, if you overuse your buffer or you use it all up, then you get your drastic changes. So things like swamps and ponds that have a lot of natural buffers, when the buffers run out, all of a sudden you have a big massive die-off because the pH changed so drastically, and all the organisms inside aren't ready for that and they die off. Those are buffers. Within your body, you have some different pH levels depending on where we're looking. So we talked stomach juice. Your gastric juices have pH of 0 to 1. So very low pH. Your urine has a pH of about 7. Saliva between 6 and 7. The water content is right at 7. Your pancreatic juice is slightly basic, a pH of 8. This range between 7.35 and 7.45, this is normal for us as an overall body. If you go outside of these normal ranges, we have different conditions that can be lethal if going too far. So acidosis, if your pH overall drops to 6.8, between 6.8 and 7.35, so it drops in this range, you have what's called acidosis. And they can reverse this using different drugs and treatments and such. Likewise, if you go on the other side, if you go up to roughly 8, you have what's called alkalosis. And we'll talk about that in a little bit. The alkali part. But that's just your body, your pH is more basic than normal. If that gets beyond these ranges, it can be fatal to you. So that's obviously not a real good thing to deal with. Well, we've talked a little bit about acids and bases. So let's talk about what they are specifically and how we kind of identify them. So when we classify something as an acid, there's some things that acids have in common. One, they taste sour. So think of lemon juice. Lemon is acidic. Lemon's got a sour taste to it. They're sticky. Think of when you spill lemon juice. So these are properties that we can measure taste-wise. Obviously, I don't want you to taste any acids in lab. Please don't do that. You can have an excess of hydrogen ions. So this is kind of what makes an acid. It reacts with metal. So if you're curious, you can put whatever liquid it is on a metal. If it reacts, there's a chance it's acidic. It also reacts with limestone. So limestone is one of the natural buffers in nature, and your acids will react with that. If you have the litmus paper, so litmus paper is a rough way to tell what the pH of something is. If you have blue litmus paper, acids will turn it red. Obviously, if it's red litmus paper, acids aren't going to change the color because it's already red. And they have a pH between 0 and 6.9, and acids are electrolytes. And think back, electrolytes are substances that conduct electricity. On the flip side, we have bases. So bases have a bitter taste. Think of the time when you got in trouble with your parents and mom put soap in your mouth. Soap is a base, has a bitter taste. It's slippery. Again, think soap. Has an excess of hydroxide ions. So hydrogen's got the excess hydrogen. Bases have hydroxide. They are proton acceptors instead of proton donors. They don't react with metals. They also do not react with limestone. They turn red litmus paper blue. So again, if you had blue litmus paper, it's already blue. Not going to do you any good to put a base in it. pH between 7.1 and 14. If it's a strong base, we'll talk about these later, it is also an electrolyte as well. Those are some different properties between acids and bases. To close up today, I would like you to think and be able to answer the questions of what is the difference between acids and bases chemically. So what do they do when placed into a chemical reaction? That's number one. Two, what are buffers? What do they do and what are they made from? And then last but not least, name 3 properties of acids and 3 properties of bases. Thank you very much for your time and attention today. I look forward to working with you as we progress through acids and bases, and I will see you tomorrow.